Welcome to week one or episode one of AP Chemistry Review with Mr. Queen. And I am Mr. Queen, of course. Just trying to make a set of videos to help out students, whether you're a former student of mine, you're a current tutoree, or you're just a random person coming across this on the internet, desperate for study resources. This video is for you. So hopefully it gives you a little bit of a review. I'm trying to do these at least once a week. Hopefully some live sessions where you can kind of come with your questions and we can kind of work on them live. Of course, if you ever have something you wish you had more detail on and you just wish someone could kind of give you a 5 to 10 minute little lesson on it, shoot me a message and have no problem doing that to kind of help you out at an individual level. That's what it's all about, is just helping this whole process be a little bit easier. All right, so before we get started, I'm just going to go over a little bit about what these series of videos is going to look like. I'm going to try to break it down week by week leading up to the AP test, covering a different unit each week. And for each subtopic within that unit, such as you see over here on the right-hand side, moles, molar mass, mass spectroscopy. Yeah, so those are the subtopics, and at least hopefully be able to touch on each one and possibly show you like an application or a problem. Of course, I can't go over everything that's on the AP test. That's what you're supposed to have been doing for the past year to 2 years to your entire science education up to this point. But we can at least give some examples of things you might see. And along the way, I also want to point out, I'm trying to do my best to listen to what different teachers have to say, different people involved with testing have to say, and of course, the official things that College Board has had to say, especially in the past few years, of changes and edits to the test. There are a lot of topics that just aren't going to be tested on anymore. And to be honest, whether it's AP chemistry or any of the AP science, any AP subject, there is just always too much to cover. If not all of it's on the test, then heck, then not all of it really needs to be our top priority. A lot of your chemistry teachers, they are awesome, amazing people. I feel like they've taught me a lot, but there are a few who kind of are stick to the old school way, which is maybe to focus a little bit more on, well, if you just know everything, then you'll have to do good on the test. And sometimes I think if your goal really is just the test, maybe that isn't the best strategy. So that's what I'm going to try to focus on with you, is breaking down some of this information that College Board puts out there, as well as we move through the review each week. And all this information is out there for you for free. So it's designed mostly for teachers, but you can use it as a student as well to guide you on the types of topics that are on there. You can see that they're not all weighted the same. We'll see on this next slide that they're not all weighted on the same type of questions either. So certain sections for your response versus multiple choice have different percentages of different topics. So just want to kind of put that out there so that you are aware of that, and that let that guide you. You want to be smart in the way that you study, right? Like, and I do know that some of you guys have AP teachers that are like, no, you need to know what magnetism is. You need to know who Jean Dalton is. You need to know these nuclear chemistry. You need, and I don't care if it's not on the AP exam. I want you to know it, which is cool. That's awesome that they're fostering that love and giving you like for chemistry and giving you like this full educational experience. But in reality, most of you guys are like really stressed out and just like worried about college all the time, which there's more to life than that, but I get it. So you're like, right, let's just like do some weird, crazy metaphor. You're like, the United States in World War II, you're fighting this war on multiple fronts. You got the Nazis, who are your GPA, and it's dictated by your teachers and your performance in school. And then you've got like the other front and like the Pacific theater, where you're battling against the AP scores and you want to make sure you get a good score in there. And it doesn't matter if you had an A in the class and you get a 3 on the test, or it doesn't matter if you get a 5 in the test and you get a C in the class. And then you finally beat both. That's what you're going to be like, Mr. Queen, thank you. You saved us. You taught us how to win on both fronts. And then you're like, I'm going to get into college for sure. And then you realize after the war is all over, or you thought it was over, the real enemies were the Russians, which was the college essay you didn't put any energy into. So again, these are all just scores. Like, dude, don't trip on one AP score or one GPA point or point, decimal point. Focus on that essay and screw up your life a little bit so you have a really good like recovery story. I think that is very powerful these days. So moving on, that's my own little personal advice. Let's go into our first topic of the day, which is going to be moles and molar mass. And so what is molar mass? Is it the mass of this beautiful thing right there? Sorry if this grosses you out. I guess that's just the biologist in me. But let's talk a little bit about moles and molar mass. And before we do that, I do want to mention a topic I noticed a couple of students were a little unsure of recently, and that was when the topic of AMU came up. And they were like, what is that? And just in case you forgot, that is atomic mass unit. So technically on your periodic table, all those little numbers underneath those atomic masses, those are given in atomic mass units. Like, oh, what's an atomic mass unit? So an AMU is like one proton is equal to one AMU, or one neutron is equal to one AMU. You're like, hey, that's pretty handy. This gives us like a unit of measurement that's like calibrated to one of the basic like particles of reality. Like that's pretty good. But then you start to think about it. Who measures an AMU? Like we don't have any scales in AMU, or maybe they do, but like, and even if you were going to use a scale for AM, like just of actual AMU, it's like, who wants to measure one atom? Like you've got a whole pile of this stuff. So that's what an AMU is. And you're like, well, how the heck do we use an AMU? This whole time I just thought it was grams, and you are right. You're kind of allowed to do that, but that's because there is this magical number called 6.022 times 10 to the 23rd, also known as Avogadro's number. And what does this number mean? Well, sometimes we call this number a mole. A mole describes is a measurement of something. So if you I don't know you I don't think a single person could have this many moles, but you could have a mole of moles on your body. You could have a mole of atoms. You could have a mole of forks. You could have a mole of grain of sands. It's a unit measurement. It's like a dozen. It's like a pair. It's like a six pack. It's just a way to measure things. And the beauty of this number, a mole of protons, it weighs 1 gram. Or I think it's defined as like a mole of carbon 12 weighs 12 grams, or what the actual definition isn't going to be on the test, is what I'm trying to say. All right, so how do we use a mole? Well, we know that mole, this number, is the conversion factor between AMUs and grams. So using that idea of mole, we can actually look at the periodic table, and instead of thinking that as the AMU of it, we can think of it as the mass of it. It's in grams, and that's what we call molar mass. So molar mass is going to be the amount of grams over moles. And this concept of mole is just really important because it allows us to think of things in quantities. A really important concept in chemistry isn't necessarily how much mass things have, though the law of conservation of mass is important, is more about how many actual particles or atoms are involved and the proportions that are needed. We need to be able to kind of count the things. So mole is a measurement of, is a counting measurement is really what it is. And that gives us just a lot of calculatory ability because it allows us to talk about the amount of matter in a lot of different systems, whether those are gases, liquids, solids, solutions. We can also refer to like energy and like, oh man, mole can just goes everywhere. So in general, what I'm trying to say, if you've never heard of the mole by now, I don't know what you've been doing for all of these science classes, but that's cool. You still have a chance to figure it out. Let's do it right now. So a mole is essentially an amount of something, and a mole is very useful because we can go from molecules and atoms, which are measured in AMUs, up to moles and then to grams. So moles is our central kind of piece of our central node of our network of conversions. So we'll see kind of how we can use that and what we can do with this concept of the mole. So let's look at, like I said, for each one of these topics, I'm going to try to move fast, but also try to give you a little bit of information about it in case you've never heard of it, or some maybe a little tip or something I noticed about it on the test, and then look at a couple concepts about it as well. If you're like, dude, I know everything about the mole already. All right, then go to the next chapter. I think the next one is going to be mass spectrometry. So if that's your thing, and I'll see you there. Okay, so before we do that though, let's look a little bit of how to convert things between moles and grams and molecules. That should be really basic at this point if you're preparing for AP Chem, but hey, I do see students who still just struggle with dimensional analysis. And I'll be straight up honest with you. It was a lot of years ago, but when I took the AP Chem test, I don't know if the teacher just didn't say it or I just wasn't paying attention, but I never knew there was like a system for stoichiometry. I would just be looking at the numbers and be like, okay, that's about like a 4:2 ratio. And like those are grams. I'll just multiply a bunch of stuff in my calculator and I'll just get a number. And that's probably why I didn't get a 5 on the test. I did pass it. I didn't get a 5 though, but it was because I didn't have any system. So have a system. If you don't know how to do dimensional analysis, watch right now and you're going to learn how to do it. So we want to know how many, let's not do this for everything. Let's just look at molecules. So for these 3 samples, let's look at the number of molecules that are present. So the first one we have is 1 mole of carbon. So whenever we do these dimensional analysis problems, we want to basically start with whatever they gave us, and I put it over 1. And that might seem redundant, but I think it helps keep everything organized when you do it this way. To be honest, I recommend if you really have trouble with dimensional analysis to the point that you're still watching right now, I would use this method where you kind of, instead of even writing fractions, well, hopefully you don't make your lines so like ugly, but here we go. Yeah, you can kind of make a grid, and basically what each box in this grid represents is a different like fraction. So you could write that out like this as well. It would be the same thing as writing your fractions out like this. And you're like, I don't need to write 1 over. At least unless you're a pro, then it really does help keep everything organized. And this technique will not just help you convert things, it will guide you through a lot of calculations if you just understand the units and the equation. So here we go, 1 mole, we want to get this into eventually into molecules. So our plan is that the units should always match up in these dimensional analysis problems. So we've got our 1 mole of carbon, and we've got our 1 mole of carbon. And now how many molecules are in a mole of carbon? Sorry, bugging me. Well, we know that 1 mole of anything is 6.02 times 10 to the 23rd, right? It doesn't matter if that's molecules, if that's grains of sand, if it is ping pong balls, it really doesn't matter. 1 mole of anything is always equal to that many molecules of it. And that's going to be a pretty easy calculation. Then all we do at the end is multiply all the numbers on the top and then divide by all the numbers on the bottom. That's how I like to do it, at least. And we end up with 6.02 times 10 to the 23rd molecules. Okay, so let's move on to this next one that we're trying to do a conversion of. This one's a little bit different. It says we have 18 grams of carbon monoxide. All right, and I'm going to, again, same setup, a series of fractions. And the next thing I want to do is what I like to do is my last fraction is I want to figure out molecules. And now I got to figure out how to get there. Now, unfortunately, I don't know how many grams a molecule of carbon monoxide weighs. I know it in AMUs, but it's not in grams. So what I'm going to do is I'm going to use that concept of the mole that I learned, which is basically that 1 mole of a substance is equal to the grams of 1 mole of a substance is equal to the same as the AMUs of 1 unit of that substance. So I'm going to put 1 mole up top, and then I want to know how many grams does 1 mole of carbon weigh? And that's where the periodic table comes in. I can now use those AMU measurements to basically put the mass in grams. So let's see what I got. Carbon and oxygen, that's going to be what? 28 grams. And then I have down here 1 mole is equal to 6.02 times 10 to the 23rd. So I know a lot of students who go, how do I know which goes where? And well, first of all, you can let the units guide you in general. But this and this like will cancel out. This and this was grams. This will cancel out. But another problem I see students with is that they know where the moles and the grams goes, but then for some reason they want to put 28 up here and 1 down here. And how do you kind of make sure that you don't flip it when you're doing these kind of things? Well, ask yourself, does this equal 1? That's the whole point of the unit conversion. If you haven't noticed it yet, you're multiplying it by 1 a bunch of times. So 1 mole and 28 grams is the same amount when it comes to CO. So essentially, it's equal to 1. So that's the whole concept behind conversion factors. I don't know, hopefully that's obvious to you, but I know it went over my head the first time. I thought it was just multiplying random things together. But if you use that, it should hopefully guide you consistently to the right answer. So real quick, pull up the calculator, see if we can calculate this thing. And this time I am going to use my calculator, but as we move through some of these videos, I'm going to start giving you tips and tricks of how to kind of avoid the calculator, because half the test, you're not going to have your calculator. Now, they're not all math questions, but they do give questions that have some aspect of math. And then let's look at our sample C, which they already gave us to, was 3.0 times 10 to the 23rd molecules of water. So which one's the most? It was the first one. The first one was the largest amount, the 1 mole of carbon. Okay, let's move on to the next concept, which is mass spectrometry. Okay, so I was gonna say I'm not gonna go over this. I'm not gonna talk about protons and electrons and neutrons, but I guess we kind of need to know that couple of those concepts in order to really understand what's going on with mass spectrometry. One thing that I'm going to try to do whenever possible as we go over these subtopics is if I notice that College Board puts one of these exclusion statements, which is basically saying Yeah, no mass spec, but don't worry about this. I want to highlight it as well. So interpreting mass spectra, it says right there, interpreting mass spectra of samples containing multiple elements or peaks arising from species other than singly charged monatomic ions will not be assessed on the AP exam. So that might not make sense to you quite yet, but we're going to come back to that when we get to the mass spectra. But before we can do that, let's do a really quick, hopefully, summary. If you don't know this, like you can figure it out. You can still learn. There's still time, but you might ask yourself, like, maybe next year is a better year to take the AP test. Okay, so protons, right? Protons are positive. We might write it like that. We got our neutrons, and we got our electrons. And in most elements, as you can see in this cool little diagram over here, the number of electrons and the number of protons would be the same if we would say it's a neutral atom. So yeah, let's go ahead and just use the diagram of lithium we have over here. All right, so the mass number, the total number is the protons and neutrons. Usually the electrons and protons, since one's positive and one's negative, there's an equal amount of each so that you overall have a neutral ground state atom. Now, when you don't, that's something called an ion. So if you have more electrons than protons, means you have more negative than positive. I guess it would be negative. So if somehow this lithium ended up with 4 electrons and only 3 protons, it'd be like that. Or if it went the other way and had 2 electrons and 3 protons, then it would be lithium plus. So that's how we write out ions. Ions are essentially a charged particle because of the difference in electrons and protons. Another way that we end up with sort of different amounts of things is not always, but often there are more than one kind of version of the same element. So what do I mean by that? Well, protons is like the ID card of an element. Based on how many protons you have is basically your identity. If you have 6 protons, you're always carbon. Doesn't matter how many electrons you have, doesn't matter how many neutrons you have, you're always carbon. Same thing with lithium, but for 3. But neutrons can vary. So what that means is you can have something like carbon 12, which has 6 protons and 6 neutrons, or you can have something like carbon 13, which has 7 neutrons and 6 protons, or even there's one called carbon 14 with 14, or sorry, 8 neutrons and 6 protons. And we call these isotopes. And these exist in nature naturally. It's not like some weird thing that humans came up with. Like most elements have multiple isotopes of different forms they can have. And they have different amounts of abundance. So you go out in nature, 99% of the carbon you find is going to be carbon 12. About 1% is going to be 13. And about some tiny little, like 1 part per trillion or something, is going to be carbon 14. So that's just naturally occurring. So when scientists do an experiment with a sample of carbon, I mean, there are methods, I guess, they can control which isotope they're using. But in general, like a normal natural sample is going to have a mix of all of them. So what scientists did was when they wanted to represent these masses on the periodic table, which is like their ultimate toolbox and bunch of interesting information or useful information, they use atomic masses, which are actually weighted average of all the isotopes. So when you see something like on the periodic table, you see, oh, I should have an example, but if you look at carbon, usually underneath it's like 12.011. And you're like, well, how the heck did they get a fraction of a proton in there, a fraction of a neutron? Well, that's because it's a weighted average of all the other isotopes. So you end up with most of it's carbon 12, so it's really close to 12, but a little bit of it is 13 or 14. So we'll look at how we can do that in a minute after we look at a mass spectrometry reading. So why was I going over all the super basic stuff? Because you have to know it to understand mass spec, and that's always going to be on the AP test. So a mass spectrometer is essentially a device that is going to bombard a sample of particles, a sample of an element with ionizing energy so that some of them become ions. So in this case, I think we've got copper. So you have your normal copper sample and you go and you blast it and it turns into Cu plus. And okay, and then so you have the Cu plus, and some of them are going to be the different isotopes, right? They have different masses. So we use this method to separate those. So they have a charge, and then we blast it through a magnetic field, and the magnetic field, since interacts with the charge, it kind of deflects the particles or bends their path. And the based on the mass, they get bent more or less because if they're more massive, they'll be a little bit more resistant to that force, or there'll be more I guess, attracted to it. So essentially what happens here is we are able to separate the atoms, essentially a measurement of them in the ionic form so that we can see how much there is of each. And we produce something like this. This is a mass spectrometer reading, which means that 60 something percent, 69% of them were copper 63 and 31% were of copper 65. So then we can use this data to create a weighted average. So if we were doing this for real to calculate the atomic mass, we could do like, hey, we have 65 times 0.31, which is 31%, plus 63 times 0.69%, right? And then we add it all up together and we would get something hopefully pretty close to 63.55, which is like the one from the periodic table. So that's what you do with a mass spec. That's an example of how to read one, what to use it for, how it works. Now you might notice this down here. It says mass to charge ratio. You're like, wait, I thought this was just mass. So technically, every once in a while, you get some of these crazy ionizing particles. Some of them might pop up as Cu2 plus ions. And that's going to affect the way the mass spec works. Those are going to be affected by the magnetic field way more, and they're going to move in a lot more of a way than the ones with only the +1 charge. So technically, this is the mass to charge ratio. So there are all these examples where you see like these other little smaller peaks down the way, and you might have to worry about things like fragmentation. But my interpretation of this exclusion statement is that you don't need to worry about that. You don't need to worry about any weird abnormalities. It's singly charged monoatomic ions. So we're not going to worry about polyatomic ions or fragmentation or none of that stuff. So if your teacher made you learn it, that's cool that you know it, but don't worry about it for the test. If you didn't get it, then just move on. Another way of representing this is with relative abundance. I'm not really going to go over this one, but do know there is another way to represent it. Essentially, it's very similar. It's just scaled to the one that is the most, and it just puts that at 100, and it puts that at like, say what, like 20. So essentially, you do the same thing. It's just that instead of being out of 100, this one's like 20 out of 120, and this is 100 out of 120. But besides that, the calculation is the same. Okay, next up is elemental composition of pure substances. So before we can kind of get into what a calculation of this looks like, what even is a pure substance versus a mixture? So we can divide matter into these separate categories of pure substance and mixture, and even those we can break into smaller categories. But basically what it comes down to, which is which, is can it be physically separated? That's what the first thing we want to see. Are there actual pure compounds and elements here, or is it a mixture of different things? So if you can physically separate it, whether that's through some kind of filtration or distillation or any kind of method, really, if you can physically separate it, then we call it a pure substance. No, we call it a mixture. Sorry, if we can't physically separate it, my bad, it's going to be a pure substance. If we can physically separate it, it's going to be a mixture. And then within mixtures, which is the next topic we'll get into, so might as well say it now, we have homogeneous mixtures, also known as a solution. That's where everything that's mixed together is like spread out evenly. And then you have a heterogeneous mixture, which is when the composition is not uniform. Like think of like an Italian salad dressing, right? Like it's if you let it sit, it gets like all messed up. And even when you shake it, it's still not like consistent like throughout the whole thing compared to like salt water. If you dissolve salt water, it's all salt water. It's not like certain parts are saltier than others or like anything like that. So that's our general description of elemental composition. So you're like, oh, now let's look at pure substances. Can it be chemically decomposed is like our big question. So can you break it down? For example, water, H2O, that would be considered a compound. You can't separate it. You can't put it through some filter and separate the hydrogen and oxygen, but chemically, you can do reactions that will turn water into its constituents, into hydrogen and oxygen. An element, you can't do that. If you have a pure element, you can't decompose it down to anything lower than that. It's just one type of atom. So that's our definitions there. What does that look like on the AP test? Well, usually, to be honest, what they're trying to really get at with these elemental composition of pure substances is they're getting at something called empirical and molecular formula. Okay, that's what this is all about. That's how they usually want to test that concept. Of course, it's good to know other things about it, like we just said, like how to classify it, but that's usually what this is going to show up in terms of quantifiable stuff. So let's think about how to do that. Also for this problem, just to make it a little bit more fun, maybe we do this as like a different number. Let's do this as 197 grams. I don't know. You'll see why at the end. It just makes it boring otherwise. Okay, so let's do one of these questions. They ask you, what are the empirical and molecular formula? So what does that even mean? So empirical formula is like the lowest ratio of elements that you can express in a chemical formula. So I think this goes back to, I think it was John Dalton, or maybe it was another scientist who had this idea of the like law of like proportions. So like basically what he realized was H2O is always 2 parts hydrogen and 1 part oxygen, or it's always 2 grams of hydrogen and 16 grams of oxygen. That's like what it's water is always that way. So we have these chemical formula that represent those different proportions. So for example, we might have this whoops, let's do C2, C2H3. That would be the empirical formula of a lot of other compounds like C4H6 and C6H8. So what is the empirical versus the, is that right? No, that's wrong, sorry. Yeah, there we go. Okay, so these would all be, only one is an empirical formula, which is right here. And these ones are molecular formulas. This could be a molecular formula as well. So empirical formula is just the lowest reduced version of it. And when we're given in these kind of problems data about the mass, the composition or the mass percent, that is going to only allow us to determine the empirical formula. We need a second piece of data, which is the molar mass, to figure out the molecular formula. So just remember that that's the data you need. So they won't ask you it if you don't have it, if you don't have molar mass. And if you don't know what you're supposed to do next, maybe you need the molar mass. So let's see how we do one of these problems. The best way to do it is to break it down by the elements that we're looking at. So H, C, and Cl, the problem says. Compound contains 4.07% hydrogen, 24.27% carbon, and 71.65% chlorine. Its molar mass is 197 grams. What are the empirical and molecular formula? Okay, so this is going to be an example of, I'm going to tell you a time where we're going to try to do this without using the calculator. I don't know if they would give you one quite like this on the AP test, but it is good practice. So for hydrogen, we have 4.07%. How do we use percentages with like grams and molecular? What do we even start with? Okay, so we're going to start these problems by just always assuming we have a 100-gram sample. It's going to make things a lot easier. So it's going to be 4.07 grams. And for carbon, we're going to have 24.27 grams. And for chlorine, we're going to have 71.65 grams. All right, and we're going to then, like, well, it's not based on grams, it's based on the proportions of the molecules that are in it. So the first thing we want to do is switch this all over to moles. So when in doubt, in chemistry in general, convert to moles. That's my advice to you. So hydrogen, we know that it's 1.01 grams for 1 mole. And you might say, where'd you get 1.01? From the periodic table. It helps us know the grams per mole. And this one we've got 24.27. Whoops, that's not how we would do that. We want to convert that to moles as well. So we'll put 12.01. And then down here, we want to convert this to moles as well. So I think what's chlorine? 35.45 grams per mole. So this is an application of molar mass yet again. What's this going to give? This is about 4-ish. This is going to be about what? I'm going to say 2 point, maybe 1-ish. And this is going to be about 2-ish as well. So do notice I am saying ish. I don't know. You can do it in your calculator, but you're going to be pretty close. Don't freak out if it's like 3.99 or like 2.14. Like it's close enough. We're going to see why in just a minute. So if it's like 0.5 or 0.33 or even 0.25, then it's a little too far to round it. But usually for these other ones, we can kind of round if it's within like about 10%, I'd say. Okay, so what do we do with this number now? Well, that's basically told us in this compound, it's going to be about 4 parts hydrogen, 2 parts carbon, and 2 parts chlorine. So we could write this out as a formula. So I'd say C2H4Cl2. And if you're like, how'd you know which order? Well, probably it wouldn't matter that much, but usually the ordering that we use is there's carbon and hydrogen. This is more of like a biochemistry thing or organic chemistry. You always put those at the front and then you put the other stuff at the end. Okay, so C2H4Cl2. Now we're looking for empirical formula. Remember, that was the most reduced form. So we can reduce this further to CH2Cl. Hey, okay, so there we got it. That's our empirical formula. That's kind of represents the ratio of different types of molecules or different types of atoms in this molecule. Cool. Now we need to find out the molecular formula. So how do we do that? Molecular formula could be anything. It could be C4H8Cl4, or it could be something crazy like C2000, H4000, Cl2000. So like, how do we do it? That's where the molar mass comes in, the other piece of data they gave us. So there's a kind of handy little ratio we can use, which would be the molar mass of our molecular formula divided by our molar mass of our empirical formula. And that should give us the ratio of one to the other. And we can use that to calculate one from the other. So for the molar mass of that, we know of the molecular formula, we know it's 197 grams. And for the molar mass of the empirical formula, so I think it's 49. Yeah. So 197 divided by 49 is about 4. So that tells us that the ratio from molecular formula to empirical formula is 4. So we just take our empirical formula and multiply all the subscripts by 4. So that'd be C4H8Cl4. And that's our final answer. So that's our molecular formula. Okay, let's keep rolling. We got a lot more to cover, and we've already taken quite a bit of time. That's all right, though. All right, the next thing coming up is composition of mixtures, which we already went over the data. So what does a question like this look like? And here we go. It's a 1.60 gram calcium. So this is a sample problem of what like a mixture problem is going to look like. A lot of times it comes up as an impurity, or sometimes it comes up as some kind of mixture of metals. But this is a good kind of classic example of using the concept of elemental composition of a mixture, or even like molecular composition of a mixture. So what do we do with this question? We got 1.6 grams of calcium supplement, which contains 37.8% calcium by mass. The calcium is present in the supplement as calcium carbonate. So if we have a 1.60 gram supplement of calcium, and we know that 0.378 of it is calcium, and the rest of it, the total is calcium carbonate, we can calculate what number of grams is just the calcium. It's going to be 0.60. Let's just call that 5. Okay, so we have 0.605 grams of calcium in this particular supplement. The calcium is present in the supplement as calcium carbonate, okay, which has a molar mass of 100.09 grams. How many grams of calcium carbonate are in the supplement? We know how much calcium's in there, but we want to know how much of it is calcium carbonate. So if you take a supplement or vitamin, you probably know it's not like pure that substance. There's also like fillers and binders and maybe other chemicals in it as well. So what we're going to do is we're going to take the molar mass or the mass of 1 mole of the CaCO3, and we're going to put it over the mass of just calcium, which is about 40 of just calcium, how many grams there are in 1 mole. And then we're going to multiply that by the number of grams of calcium we have. So this proportion is going to allow us to kind of back calculate how much of it calcium carbonate do we have if we know how much of it's calcium. So we do that calculation. Okay, and what I got was 1.51 grams of it is calcium carbonate. So hey, then you could even figure out like, hey, how much of it is not calcium carbonate? Oh, 0.09. So that's the amount that's an impurity. That's some kind of filler in the mixture. All right, so let's keep moving. Let's move on to the next topic, which is atomic structure and electron configuration. Okay, so this is a hot topic. If we look at there is a little exclusion statement that comes with this topic in the College Board materials, and it says that the assignment of quantum numbers to electrons in subshells of an atom will not be assessed on the AP exam. So hey, good news, they are not going to ask you about quantum numbers. If you don't know what that means, great, you didn't waste your time learning it. If you do, you might say, oh, it wasn't even that hard. Well, yeah, it's not that bad. But for some students, it really is kind of troublesome. And it really doesn't help you understand chemistry, at least at the level that they're trying to teach you in AP Chem. So we're not going to worry about that. I think there's one more exclusion that goes with this, and that's going to be called the Aufbau principle, where you don't need to know about the exceptions to the Aufbau principle. But we'll get to that bridge. We'll cross that bridge when we get there. Okay, so atomic structure. So usually when you learn this in school, they start by teaching about like all these old scientists. They say, oh, this Greek guy named Democritus like thought about the atom a lot and wrote it down. And I'm not trying to discredit that guy, like that's a really cool breakthrough. And then they moved on to, like, I think Epicurus was one of his followers, and then Aristotle came along and basically ruined that whole idea and said everything was made out of four elements, and that kind of stuck around for 2,000 years, at least in the West. That's something else to notice. Like, I don't think that the Greeks are the first people to come up with the atom. There is documented philosophers and scholars and mystics and all that stuff from cultures across the whole world who have um, posited this idea, whether it was in China or India or Egypt or whatever it is. So just know that you don't really need to know that early history. For some reason, they always teach it to you in school. Rutherford and Thomson. I don't see how that's going to be on the AP exam. So don't freak out like, oh, I don't remember who did what. The reason why knowing those experiments might be useful is that some of them are going to like they might ask about the experiment, like what were they trying to discover, but they would give you background information. So don't waste your time with that. Let's get on to atomic structure though. Okay, so atomic structure, in the old days, you had Bohr. So why did I talk about the history if I said it's not important? Because I wanted to lead into Bohr. So after Dalton came along and came up with the whole atom theory, and then you got Rutherford and electrons, and then Rutherford and the protons, and the nucleus, and J.J. Thomson electrons, all that goodness. Essentially, then Niels Bohr comes along and he says, hey, what if it's more like an orbital, like the electrons like flying around like this? And that was a really good idea, and it helped explain a lot of things about chemistry, but it didn't really compete with eventually the quantum physicists or quantum mechanics chemists who came up with the what you now know as the quantum mechanical model of the atom. So that talks about orbitals that look like that. That would be a p orbital. Talks about orbitals like that, an s orbital, and then you get even crazier ones like d orbitals that are just like all over the place. It doesn't look quite like that, but it looks pretty crazy. So a question I had last time I talked about this topic was, do we need to know the shapes of the orbitals? And I'm going to say really only for S and for P. You don't need to know those crazy pictures. They look cool. They like to put them in the books and the slides, but I would say no, you do not need to understand the shape of the D or the F orbitals. Only need to understand the S and P shapes, and only limited enough to help you understand sigma and pi bonds, which is going to come in the next lesson. All right, so what is this quantum mechanical model? You've probably heard of it before. So in fact, the system that has been able to best describe what we see in the atom is this suborbital model, that there are these orbitals known as S, P, D, and F. And S has one region, P has 3 regions, D has 5 regions, and F has 7 regions. And each of these regions can accommodate up to 2 electrons at a time. Now, the whole thing is constructed from like mathematical equations about quantum wave functions, and that's really cool. If you want to understand it, go for it, but like you don't really need to know it. Just understand that these are essentially probabilities. The whole calculation was, hey, once the Heisenberg uncertainty principle, all that stuff's coming together, they're like, we can't really know where the electrons are, but we can make a pretty good like guess, and this is what we think that where they tend to be based on the calculations and the mathematics. So S, P, D, and F, what are we going to do with that? Well, we can use that to actually talk about the electron. So instead of saying like, oh, there are 2 in the inner orbital and this many in the next orbital, we can use this SPDF notation to essentially represent the number of electrons in an atom. So let's look at an atom. Let's look at let's just start with nitrogen because it's kind of smaller. And we can, if you learn about these different orbitals, you'll discover that they are kind of divided into the original kind of orbitals Bohr proposed, which we now call energy levels, maybe. So, and if we write them out on a chart, and you've probably seen something like this, it kind of breaks them down by the amount of energy that's in each one. Right, something like this, so on and so forth. And it gets a little funky after that. So these different shapes, they have different energy levels. So this would be like the 4s, and this would be like the 3D, and we'll talk about why it does that in a minute. But essentially, we can fill these orbitals up with electrons. So if we want to look at nitrogen, we see that it has a atomic number of 7, which means that in its normal ground state, it has 7 electrons. So we start filling them in. First, we're going to use something called the Aufbau principle, which is that you always want to fill in the lowest energies first. And there's something else called the Pauli exclusion principle. It's basically only 2 electrons can inhabit an orbital at the same time. So we're going to fill in this one with 1, 2, 3, 4, 5, 6, 7, and that's it. So that would be our atom right there. of nitrogen. That's how we could represent with this chart. And hey, now we represent where all the electrons are. We can use that information to help us predict things about it. But this is kind of a cumbersome format. So what we usually do is write out the electron configuration, something like this: 1s2, 2s2, 2p3. And hey, now it tells us exactly where all the electrons are, and we can use that information to predict how it's going to behave, which is always what science is trying to do, like kind of like make observations and predict stuff. However, there's other ways that we can write it, and it can get kind of complicated. Like if we jump up here and go down to, like, I don't know, like this tellurium, or even lower, like to polonium, it gets a little bit hairy because we're writing like 1s2, 2s2, 2p6, and you're like counting out, it's 84 electrons. You're sitting here, you're drawing all day, you're like going off the page. It's taking you like half an hour to do your just one homework problem. And there has to be an easier way, and there is. And there is a shortcut that you can figure out using the periodic table. So the periodic table, we can divide it into these different blocks. If you haven't learned that yet, oh gosh, hopefully this helps. It's going to make your life easier. If you already knew it, then like I said before, skip to the next section. All right, and this is the F block down here at the bottom. Why did we write that? Well, because that's where the electrons tend to be. That's why it's divided the way it is. Well, it's not why, but it's one of the many cool features of the periodic table. So now if we want to know about, like, hey, what's the electron configuration of germanium? We can see, like, oh, it has one. So this one's, helium's an exception. It should be kind of over here. Has 1, 2 in the s orbital. And then the next s orbital has 1, 2. So we would have like 1s2 and then 2s2. And then 2p6, 3s2 going across, 3p6, 4s2. It's going to get a little weird right here. You would say like, oh, this must be 4d10. It's actually 3d10. The D block is like a little bit different energy than the other ones. So it actually goes out of order right there. And that's why we do represent it the way we do, or it kind of is like its own block. And then we have P12, so 4P2. That would be our electron configuration. It gets a little bit cumbersome. Scientists are pretty lazy. They always like little shortcuts and stuff. So we can rewrite this also using something called the noble gas, like kind of shortcut configuration. So to do that, you basically look backwards from germanium and you find the last noble gas, which was argon. And we can just write argon and then just write the rest after that. It kind of tells whoever's looking at this, like, yeah, just imagine all the stuff that would be up to argon, and then here's the new stuff. So 4s2, 3d10. All right, great, cool stuff. So it's pretty good. The only like little special rules is that the d orbital, if you don't understand that why it's in the lower energy state and all that kind of business, just remember at least that the d orbital is always -1. And if you do get down here all the way to element number 57, you get into the bottom little section over here, then know it's that it's F -2. That's really what you gotta know. They can ask you to figure these out for ions. In that case, you've got, if it's a negative ion, that means you got one extra electron. So you would do everything the same, but you'd put that one. So sometimes that could mean that essentially the electron configuration might look like say for example, of a fluorine ion that has one extra electron, it's got 10 electrons, or a neon atom also has 10 electrons. So they're actually going to have the exact same electron configuration, and we call that isoelectronic when they have the same amount of electrons. So just a vocab word to throw at you if you feel like you didn't have enough going on already. All right, so that is essentially electron configurations. You're like, wait, I thought there's some special elements that have special rules. Well, you are right. There are some rule breakers here. There's like chromium and copper, which actually start filling up the later orbitals instead of filling up the earlier ones because it's more stable. But hey, we're not going to get into those exceptions because guess what? In 2 sections from now, we are going to see, hey, this one, and it says, don't ask me why it's on this slide. It's because that's how it's organized in the AP College Board materials. Writing the electron configuration of elements that are exceptions to the Aufbau principle will not be assessed on the AP exam. So you don't have to worry about copper and chromium. Like, that's an exception to the Aufbau principle. Don't stress on it. Okay, so our next topic is going to be photon electron spectroscopy. This is a method of essentially, we don't even know exactly how it works. I'm not going to ask you about that, but you're essentially like blasting a atom with photons of different energies, and you're seeing like which ones bounce back and which ones don't. That's at least how I understand it. But basically what it helps show us is it gives us sort of like a picture, a readout of the electrons in a material. And it gives us data in kind of two ways. It gives us data about the relative number of electrons, essentially how strong the peak is, how strong a certain set of photons are bouncing back, and then also the binding energy as well. So one thing I noticed immediately when I saw this graph for the first time is why the heck is the big number over here and the zeros over here? But we're going to see that in just a minute. So before we can kind of understand how this shows us more information about the electron configuration, we have to think about a little bit about like what does it mean by binding energy and what would control that. So this is our first appearance of everyone's favorite and most important law in explaining atomic trends and stuff is Coulomb's attraction. Okay, so this is, you're like, what does all this mean? Charge 1 times charge 2 over distance squared equals the force. That's basically describing the force of the electrostatic attraction. And force is going to be proportional to energy. I think if you do your physics, force over distance is energy. And the Q1 and Q2, you're like, oh, what's this all about? Well, we're always comparing the energy of an electron. So that's always going to be, one of them is going to be -1 electron. So we don't really need to think about both charges. On the top, really just think about, I like to think of it like this, where Z is the effective nuclear charge. So why is this important to knowing binding energy? Well, if you have more protons, they are going to pull an electron tighter. Okay, that makes sense, right? You have the bigger product of your charges. Also, if you have more distance, then again, it's going to affect the energy as well. So essentially what this allows us to do is by knowing the binding energy of these different groups of electrons, they essentially give us information about the distance and maybe even a little bit about the orbital. So I'll show you how in a minute. So this one, if you notice, now we start to see why the graph is like this. How do we read one of these things? This represents a set of 2 electrons because we see about a relative abundance about 2. So it'd be 1s2, and this represents 2s2, and this is going to be 2p4. So we don't actually know that it's 2. This is like convenient little lines. Don't trust those lines. All we know is the relative abundance, but we do know when an s orbital is full, it has 2. And we also know that the s orbital, 1s, is going to be the closest to the nucleus. So it's going to have the most force and most energy in that bond, in that interaction. So that's why we put it a lot higher. So this is how we read these. We essentially can assign the electron configuration based on that. So from reading one of these, a complete one, you should be able to determine exactly what element it is. This is going to be 1s2, 2s2, 2p4. What element is that? Oh, that is oxygen. So this is actually a PS spectrum for oxygen. So know how to read these, know how to compare them, and also know what I'm about to go over with you, which is the other type of question they like to ask, which isn't just to interpret it, but to explain some of these like differences. So if we notice here, this is a photon spectrum of just the 3s electrons. So this isn't the complete thing. They just isolated just the 3s electrons of sodium and calcium. So if we look on our periodic table, we're going to notice that sodium I think it has 11 protons for sodium, and calcium has 20 protons. And if we look at the electrons, it should be 11 and 20 as well. But we'll see that sodium has up to 3s1, but calcium goes all the way up to 4s1, so which means it definitely has a full 3s2. So that's the information that we need to be able to analyze this problem correctly. The question says, why is there a difference in intensity and position of the signals? Well, first up, the intensity makes sense because in calcium, we have 2 3s electrons, and in this one we only have 1. So that's why it's twice as big. Now the second part is, why is there a difference in position of those signals? Well, what else is different about these? The number of electrons, that's true, is different, but also their number of protons. And since calcium has more protons, it's going to have a stronger interaction with it based on the Coulombic attraction, and it's going to pull and hold on to those electrons even tighter. Okay, so because of that, the binding energy is going to be higher because there's more protons hanging onto those electrons. Okay, so that's the other way that you can interpret it. So be able to not only use it to label, but also use it to describe like why things are different. Okay, Next topic, we're getting close to the end. Hang in there with me, or jump ahead to the next chapter, or go to the go to the unit 2 if that's your thing. Let's talk about periodic trends. So there was an exclusion statement for this in the AP materials, and that is electron configurations. That's okay though. We don't really have to worry too much about that. Periodic trends are like those classic questions, like which one is going to have more atomic radius? So what are like the classic trends? Atomic radius, effective nuclear charge increase. They sometimes have that. Electronegativity increase, ionization increase, affect electron affinity. So these are some of the things, and I guess that get kind of are considered periodic trends. And why are they called trends? Well, two things you need to know about this. The first one, I would say memorize a chart like this. You're like, wait, what do you mean? My teacher said I shouldn't memorize anything. Yeah, that is true, but you want to be rapid fire on these. You want to immediately go, these are no-brainer questions. You see two elements, you're going to be, oh, that's the bigger one. That's the more electronegative one. You don't even have to hesitate. And the way you're going to do that is use these these periodic trends. So for example, when it comes to size, helium is our little baby one, and way down here, we have the big boy, francium, okay? So in general, atomic radius increases as you move this direction, as you can see in the diagram. The other thing is electronegativity, a little bit different. Electronegativity is a different kind of measurement. So if you don't know what these mean, you definitely want to understand electronegativity and ionization energy, but especially electronegativity. Fluorine is the most electronegative element, and it's just a measure of how, at least the way I understand it, is how easily it attracts electrons. Okay, so fluorine attracts electrons the most because it has an open position in a very low shell, which means that it has a lot of strong interaction with the nucleus, which is positive. So this is our most electronegative. This is one of our least electronegative, and the trend goes that way. Okay, that's supposed to be a diagonal line, not some weird curvy guy. So know them like that. Know those shortcuts, but at the same time, be able to explain those shortcuts, and all of them are going to come back to the whole Coulomb's law situation. Okay, so for example, why is fluorine smaller than oxygen? Well, fluorine has more of an effective nuclear charge, right? It has more of, I like to just call it Z, it has more effective nuclear charge. So that means that it's going to have more force on its electrons. It's going to pull them tighter than oxygen, which has a little bit less effective nuclear charge. Now, the other thing we can do is look down at, hey, why is fluorine and chlorine? So why is fluorine smaller than chlorine? You said it's all about effective nuclear charge. Chlorine has way more protons. It's probably pulling on a lot more. But hey, there's a lot more distance between those energy levels. Like this one has its electrons way out in the third energy level. So it's going to be having a harder time hanging on to those. So it's not going to pull them in as close to itself. You want to make these explanations in the FRQ, or even if there's a multiple choice question, using Coulombic attraction. That's what you want to use. It can be either positive or negative. Electrons can do a Coulombic repulsion, I guess, like if they're both negative, right? Don't rely on some weird thing about shells or electron shielding. It's really not the right way to go. You're going to get the most points if you can accurately use Coulombic attraction to explain these. All right. One last thing, I wanted to go fast, but this is really important to mention. Size of atoms, ionization radius of ions is a little bit weird because our cat ions, and those are our positive ones, right? Like cats are positively adorable. That's how I always remember it. And then these are our anions. Their ions are different, and we can go back to Coulombic attraction to explain why. So for example, lithium ion, Li plus, on over here is smaller than just regular old lithium. And why is that the case? Well, it has one less electron. So if you think about its like little orbital thing, we're going to go old school and do Bohr here. But I guess those could be s orbitals. It's 1, 2 electrons and the third electron in lithium. And it loses this guy. So now, hey, it's outside level. Well, first of all, it doesn't even have anything in the energy level. And then since it's not so far away, it's not going to be pulled on less by the nucleus. So in that case, the ion will be a lot smaller. Then why are the anions? Well, now we get to kind of bring in this concept of electron repulsion. So let's use fluorine for an example. We have 1, 2, 3, 4, 5, 6, 7 electrons. And an eighth one wants to come in here. And it does. And now it's a lot bigger. Why is that the case? Now, a lot of students say, oh, It's because like the proton has to spread out its positive charge to more electrons. And you're like, I guess that makes sense from like a very like kind of scarcity mindset. Proton's not like it's not like it only has so many children it can love or something. Like this Coulombic attraction is an individual between any 2 points of charge. So by adding an eighth electron, it's not that it waters down the positive charge. What's really happening is this electron's around all these other electrons and they're all pushing on it. It's like, get out of here. We hate you. We're also all negative. We don't like each other. So the reason why we see an expansion there isn't because that the proton's not strong enough. It's because there is a enhanced repulsion because there's more of the same charges being added. Okay, so just remember that when you get to that one. All right, we're almost done. Last topic of the day is valence electrons and ionic compounds. I guess that's kind of like two topics, but let's just lump them all together so we can call it a night. Okay, so first of all, what is a valence electron? Valence electron is the electrons in the outermost energy level of that atom. Okay, so what does that mean? So we can again think about it like, oh, hydrogen, it has, even using the S model. So let's think of hydrogen has one S and it has one electron. So we would say, hey, in your outermost level, your highest energy level, not your highest energy orbital, but highest energy level, you have one electron. That would be saying hydrogen has a one valence electron. Let's look at another one. Let's look at oxygen. So for oxygen, we've got our 1s, our 2s, and our 2p orbitals. So we've got one electron, two electrons, three electrons, four electrons, 5, 6, 7, and 8. Okay, so what can we do with that? Oh, in our highest energy level, which is the energy level 2, we have 1, 2, 3, 4, 5, 6. Right, so we have 6 valence electrons. And since what we kind of have realized, or experimental over long periods of time, from a long time ago, is that atoms actually prefer to be in a state where they have a complete outer shell, which means that they have 8 electrons usually in their outer shell. That's when they're at the lowest energy. So a lot of times we say like, oh, it loves to have an octet. Well, it's just an atom. I don't know what it really loves or likes, but what we can say is that the state where it has those electrons, it's at a lower potential energy, and everything kind of likes to be going to an energetically favorable state. So how do we use this? What's the point of all this? Okay, so based on the number of valence electrons is how an atom behaves. So oxygen, which has 6, now I'm drawing Lewis structures, I don't mean to scare you if you haven't seen those in a while. And then I'll draw, oops, I don't even think that's the right way to draw it. I just wanted to draw that has 6. I ain't trying to draw a perfect Lewis structure. Okay, so we got oxygen and sulfur, and they both have 6. And what this means is they kind of have like an equal amount of valence electrons. So the way that they interact with other atoms is going to be similar. What scientists have shown is that this trend of periodicity is that in each column going down, there are a lot of trends in how those atoms react. And it's based on the number of valence electrons they have. Okay, so that's kind of an important concept to know, is that the number of valence electrons is going to dictate a lot of the chemical reactivity and behavior. All these elements over here are very reactive, the alkali metals, because they very easily lose an electron. And then these are very reactive right here, the halogens, because they easily gain an electron. So that means that it's energetically favorable for them to react with other particles, other atoms. The noble gases are infamously non-reactive, so that's why they're noble, because they're like everyone wants to be like them, right? So how do we use this idea? Why is it important? So for example, fluorine has 7 valence electrons. Oh, one last thing. If you didn't know this shortcut yet, please learn it right now. So you can use the periodic table to kind of help you know like how many valence electrons there are. 1, 2, we're going to skip over the transition metals, 3, 4, 5, 6, 7, 8. We can kind of think of it that way. It's kind of an oversimplification, but we'll go with it for now. So fluorine, for example, has 7. 1, 2, 3, 4, 5, 6, 7. And it really wants to have that more energetic state. So it can steal electron from something else and get right there. And what that does, now that it's more negative, there's still only 9 protons, but now we just added a 10th electron. The other 2 electrons are in the lower level. So we write this as F minus because it has more negative charge than positive charge. So we can also kind of use this valence electron concept to predict what kind of ions will form that are the most energetically favorable. So for these substances, they would rather lose their electrons. That's the fastest way to an octet. Carbon's kind of like a special case. It could lose them or gain them, could care less. This row usually makes -3, -2, -1, and usually we don't get ions from our noble gases. So this is really helpful because we can predict the type of ion that will be made. So carbon is like 4+. That's kind of weird. Nitrogen is like a 3-. Magnesium is a 2+, right? So hopefully you know that already. If you didn't know how to label it like this, you were really counting electrons and protons. Hopefully that shortcut's going to help you. The periodic table is like your ultimate toolbox when it comes to AP chemistry or chemistry in general. Okay, so as we try to wrap this up, how does this all apply? And one other thing, you skipped something, Mr. Queen. You skipped all these ones. You just act like they weren't even there. How mean. Okay, so the issue is here that these transition metals actually can form more than one type of ion usually. That's kind of energetically favorable. So a lot of these, like iron, could be like make an Fe2+ or an Fe3+. This could be like, not zirconium, but there are some other ones. Whoops. We don't have to go through all of them right now, but like a lot of them have 2 or 3 forms that are the most favorable. So just sort of be aware of that. And the reason why it's important is it's going to come up when we go to ionic compounds. There is some weird stuff that goes on with elements, like pretty much after we get 2 rows down, that involve like expanded octet and exceptions to the rules. And I'm not going to tell you that you don't have to know them because you do, but we'll talk about that next video. All right, so the last thing we're going to talk about is ionic compounds. So these are compounds like a new thing for us, I guess, where 2 atoms actually sort of bond together. So we're going to look at the ultra classic example of sodium chloride. And in this case, chlorine is so ready to accept that electron. It would be in a lower energy state, and sodium would be in a lower energy state if it lost that electron, that it actually goes yoink and it takes it. It's electronegative enough to kind of steal that electron. So now sodium lost its electron. It is more positive because it lost negative charge, and chlorine's more negative. And now this positive charge over here and this negative charge are actually attracted to each other, just like positive and negative are, just like positive and negative ends of a magnet. And it's going to form a compound called NaCl, and it's held together by the attraction here. It's not sharing electrons. This one stole it, and now they're attracted negative and positive to one another. And then we can name this compound, and what we name it is sodium. So here's our naming convention. We take the name of the cation, the positive one, and we put that down, and then we put the second name, chlorine, but we delete the ene, and we just write "ide." We add "ide" at the end, okay? And that's how we name these ionic compounds. Sometimes comes out a little bit differently. What if we had something like calcium chloride instead? So calcium has 2 valence electrons, and chlorine has 7. So chlorine could steal 1, but now chlorine's kind of happy because like it's at a most energetically favorable state. So we have to remember that usually, actually pretty much always, we don't just have one atom of something. We have a whole bunch of it. So another chlorine could come by and steal that. What would we end up with? Well, we'd end up with 2 positive calcium since it lost 2 electrons, and one negative chlorine on both of these. So how would it bond? How would we write it out? We would write it as CaCl2, and we would call it calcium chloride. So we didn't call it calcium 2 chlorides or nothing like that. We just call it the first name and the second name, but we change it to "ide." It doesn't matter how many there are. But do notice that they need to sort of balance out the 2 positive and the 2 negatives to make a formula unit. So we'll look at one more example of it it's a little bit hairier. So let's look at magnesium nitride. Not even a thing, magnesium nitride. So we did it before. Now we can use our shortcut. Magnesium is 2+, nitrogen is 3-. And we have to figure out how many do we need to like make this all up. And we can do, it's not that hard of math, but there is a shortcut. It's called a crisscross method. And you just kind of crisscross these numbers. And that's going to give you Mg3 and N2. You don't got to do any math in your head. You just do the crisscross and you've got the compound. So what would we name this? We would call this magnesium nitride. Okay, so the only exceptions you sort of got to know to these ionic naming conventions is when we have one of those transition metals. So like I told you, some things like iron can come in more than one form. So we could have iron 2 plus, iron 3 plus, and they could both interact with oxygen, which is usually a 2 minus. And using our little crisscross, and then for this case, we get Fe2O2, but we want to reduce it to its lowest form. It's kind of like empirical formula for ionic compounds. It's called formula unit. And then this one would be something like that. So notice that when you have a different ion, you build a completely different compound. So we would have to name these differently. So the first one, FeO, FeO, is going to be iron 2 because it had a 2 charge oxide. And Fe2O3 would be iron 3 oxide. Okay, so that's the naming convention there. Be careful with your transition metals because all of them have more than one state. I think there's a couple like Ag plus and like zinc 2 plus where it's pretty much always the same, but most of the metals have multiple ions. So be careful when you're naming them that you are naming them correctly. But aside from the number, it's still the same concept. You write the name of the element of the cation, and then you write the ide of the anion. The only last thing to mention with ions is there are, of course, your polyatomic ions. But if you've gotten this far that you're watching videos reviewing for this, well, again, I don't want to judge if you really kind of fell behind because it's not about what do I need to do to catch up. It's about what do I need to do next. So polyatomic ions are ions made up of multiple atoms. You got to know them. You got to know their names. I know there's methods like, actually I just learned this recently, like Nick the Cam 8 clams and Phoenix. I don't really know. I don't really know it, so I'm not going to teach it to you. But if that helps you, it helps you. When I was in school, like, I don't know, we still use something called flashcards, like physical. So I just wrote them all in flashcards and read them on the way to school and on the way home from school for like couple weeks, not even a couple weeks, like a couple days, and then they just kind of stick with you. So just memorize them now, especially if you're ever going to take a science class again, whether that's bio or chem, like you're going to need it. And I think that's sort of it. So thank you for tuning in today. Hopefully you found some of this video helpful. Hopefully I can whittle these down or maybe break them down into like shorter videos because like, whoa, this got a little bit long, but that's okay. Hopefully you found it helpful. If not, let me know why. Let me know how it would help out a little bit more. Next time, we're going to be covering molecules and bonding, so hopefully you find that helpful as well. Have a great night and like and subscribe if that's your thing. You can find me on Instagram under the same name, Mr. Queen Science, and same thing for Gmail. So reach out if you need help or you have a specific request or any kind of constructive feedback on this channel. All right, thanks and have a great day.